Hello everyone and welcome to the class of Econometrics 2 Econ 333. I'm Yasser Saeed and today we are going to study the problem of unit root and how it causes spurious regressions. So basically today's outline is single point, that is unit root and the problem of spurious regression. In the previous lecture we covered a little introduction about the unit root, what unit root is and what characteristics are required for a data to be stationary. So today we are going to see if the data is not stationary, what will happen. So let us start with the lecture. Most macroeconomic time series are trended and therefore in most cases are non-stationary. For example, if we take the data of GDP, the money supply or CPI for any country, we will see that they will have a trend. They will continuously rise or decline. So the problem with a non-stationary or trended data is that the standard OLS regression procedure can easily lead to incorrect conclusions. It can be shown in that these cases the norm is to get a very high R square, and the value of R square is sometimes even greater than 0.95, and beside this we will also get high T statistics, and these T statistics can be greater than 4. So while the variables used in the analysis will actually have no relationship with each other. Then many economic series they have typically an underlying rate of growth, which may or may not be constant. For example, GDP grows at a certain rate, but that rate also changes over time. And if we look at the data of prices do increase each year, so they have an underlying rate, and the same is true for the money supply, and all of these three are usually growing at an annual rate of varying level. So such series are not stationary, and the mean is continually rising in these series. However, they are also not integrated. We may take a number of differencing for these variables. We may take first difference, we may take second difference, third difference, but sometimes they will not get stationary. So this gives rise to one of the main reasons for taking log instead of differencing for a data before subjecting it to a formal analysis. If we take the log of a series which exhibits an average growth rate, then we again return into a series that follows a linear trend, and that linear trend is integrated of first order. This can easily be seen formally. Suppose that we have a series, and we call it x, and we assume that it grows at a 10% rate annually. So if we take data for that, we have a series x t and xt equals to 1.1. 1.1 basically means 1 is the actual value of xt minus 1, but 10% growth, that is shown by 0.10. So x t minus 1. So this is our let's say equation. Xt grows by 10%, and the value of xt minus 1 is its lag value. So what happens if we take log on both sides? If we take log on both sides, we will get log xt, that equals log 1.1, because whatever is multiplied in logrammatic form, it is converted into addition. So log 1.1 plus log of x t minus 1. So basically, after taking log, we have converted this equation into a linear form. We have, let's say this is our y term for a linear equation equals a constant term alpha plus 1, which is the slope, or we may say beta value equals to 1, and log xt minus 1 translate into our x term. So our equation is linearized. Now log 1.1, which actually contributed to the growth, is now a constant term equal to alpha. Each and every time we take the log of 1.1, that will be a constant value. And because of taking the log, now we have removed the element of growth, and we have made this equation or this relationship as stationary. Then in the presence of a non-stationary, the results obtained from a regression of this kind are totally spurious, and this term was introduced by Granger and Newbold in their research paper in 1974. Therefore, this word is now commonly used. The intuition behind this is quite simple. Over time, we expect any non-stationary series to wander around. So over any reasonable long sample, the series will drift either up or down. If we then consider two completely unrelated series that are both non-stationary, we would expect that either both will go up, or both either one of them will go up and the other will go down. If we then perform a regression of one series on the other, we would find that either a significant positive relationship if they are going in the same direction, or if they are going in the opposite direction, then we will find a negative relationship between these variables, although they are not related. So a spurious regression usually has a very high R square and t statistics that appear to be providing significant estimates, but the result may have no economic meaning at all. This is because the ordinary least square estimates may not be consistent, and therefore the test for the statistical inferences are not valid. To see this, the significance of the problem, uh, Granger and Newbold in 1975 constructed a Monte Carlo analysis generating a large number of YT and XT series containing unit root. We can replicate that. The formula for YT, a series YT, and in order to have it a unit root, we may say that it equals to 1 y t minus 1 plus e. This is the error term relating to the yt. So we apparently we can see that this equation has a unit root. Then again we generate another series and we call that xt, and xt is equal to xt minus 1. Again it has a unit root plus e, the error term that is related to xt. So these two series are generated. A large number of data has been generated for these two series, and the error terms here, this one and the second error term, They are artificially generated normal random numbers. They are random numbers, and they are generated artificially and then added to the basic equations. So since yt and xt both are independent of each other, any regression between them should give insignificant results. You see, we haven't generated yt based on any yt over here. Similarly, xt is not generated based on any the value of xt over here. Both are independently generated. But when the two researchers, the Granger and Newbold, regressed various yt's and xt's, they run regression. Let's say they ran a regression of yt is equal to alpha plus beta xt. What they got was pretty surprising, and that was in 75% of cases the relationship between yt and xt was found significant. In 25% cases, this relationship was not that significant, but in 75%, the result were quite significant. And they had a very high r square. The value of r square was high. Similarly, the value of DW, the Durbin Watson statistic, that was very low. And Durbin Watson statistics is calculated for autocorrelation. The value of Durbin Watson statistics is better if it is near to 2, but that was very low. And to the level that the R square, they were usually higher than the DW statistics. So this was a kind of you may say that a problem that they have identified. uh, Graphically they have also shown the relationship between the two variables, but if let's say these two series, the two that we have drawn, and if you plot them, you will get a significantly positive relationship, but in reality these two were independently generated. So the Granger and Newbold, they suggested a rule of thumb for detecting the spurious regression. What is the rule of thumb for these spurious regressions? The rule of thumb is that if r square is greater than uh, if r square is greater than the dw state, or r square is statistically equal to 1, very near to 1, in these cases the regression must be spurious. If any of these two cases has been found, we may say that the regression will be spurious. So let us state this problem in a slightly more formal way. The, the source of spurious regression problem arises if two variables x and y both are stationary. Then in general any linear combination of these two will be stationary. Whatever combination, if you have x and y and they are stationary, then x is equal to 5y, that will be stationary. X is equal to alpha plus 7y, that will be stationary. Any combination will give you a stationary relationship. But one important linear combination of this term, of course, the equation error. And so if both variables are stationary, the error in the equation will also be stationary and have a well behaved distribution. Let's say like in this model, if we add the error term, this error term will also be stationary. If x is stationary, y stationary, error will be stationary. But if any of these two variable that is not stationary, the error term will also not be stationary. So, if in fact, as a general rule, and this will not always be true, the error itself becomes non stationary, and when this happens, the basic assumption of the OLS is violated. Our assumption for running a regression equation is that um, it should have a mean equal to 0 and its variance should be constant. The mean of a non-stationary data is not equal to 0 and its variance also goes to infinity as the data proceeds. So basically what happens, the regression equation is then not valid. It violates the basic assumption. The data will not be best linear unbiased estimate anymore. This basically violates the assumption of our ordinary least square. So the simplest way to examine the behavior of the error term is to rewrite the equation, the error term equation, and say that Et is equal to Yt minus beta 1 minus beta 2 xt. We have written the equation in the form of the error term, or then excluding the constant beta 1 because that doesn't plays a lot of role in our interpretation of the data basically. So et then becomes yt minus beta 2 xt. If yt and xt are generated by our earlier equation in the equation 1 and 2, uh, here that we have discussed, our equation 1 and 2, if yt and xt are generated by this equation, then what we obtained here is that ut will equal to summation I equals 1 up to t e y I minus beta 2 summation t I is equal to 1 to t and the error term related to x. So these two error terms, y will equal the ut term, sorry, we have the et term over here, that will equal to our equation number. Let's say if we number them again, 3 4, so this will be our equation number 5. So from this equation we see that the variance of the error term will tend to become infinitely large as t increases. When t increases, the variation in the error term that will also rise. Then moreover, the error term has a permanent component in that the expected value of et plus 1, the expected value of et plus 1, that must equal to et for all the values of I. This should be true for all values of I, and that is hence the assumption of the classical linear regression model is violated here. Therefore, the NET statistics or F statistics or the value of R square, they all are unreliable. So that's all about the spurious regression and the unit root. In the next lecture, we are going to test for the unit root. How can we see if the data has any unit root or not? If you have any question, please do ask about it. Thank you very much.